Hi everybody, we are still in the middle of the Debye model. And in the Debye model, so first of all, we managed to obtain that the Hamiltonian of a solid is going to be sum I goes from 1 to 3n of 1 half here of z I dot squared plus d I divided by m, you'll have m over here, of z I squared. Something like this. And we said that bi divided by m is the omega I squared. And basically, those coordinates, z, are degrees of freedom. They do not specify any specific position, but they specify particles or quasi-particles that we call phonons. Okay. And so our plan was to describe everything, when I mean everything, to address the problem of solid and the specific heat of the solid when we use for energy and the description of energy those quasi-particles, those phonons, which are normal modes of the solid. Okay? And we can write the total energy as a sum of energies of all the different phonons that we have inside. Okay. Question was, what is this di divided by m? Because in general, well, we obtained this as a sum terms in a matrix, and this matrix was huge, right? 3n by 3n. It represented the potential of and the interactions of all the different atoms and particles that we have inside the system. We don't know how microscopically obtain those terms. So what we started to do, we tried to obtain it statistically. In a sense, well, we can count the number of states or the number of different modes that can survive in the system up to a specific omega. Okay, so this is what we've done. We counted the number of different standing waves that we have in a system up to some frequency omega, right? Then we have taken the derivative of this expression, and we obtained d of omega, which is density of states. What it means how many states, how many standing waves are corresponding to a given omega, right? So we're assuming we do know that there is a specific number of different modes, right? But we cannot obtain this exact number. What we do, we assume a continuum spectrum of all the different modes, and we compute the different weights or the different densities of those modes on the line of omega. Okay. Now, this d of omega, we got a form for it. Let us see, what was the form? It was v, let's find it. So it is volume divided by 2 pi squared multiplied by something. I never remember this guy. Yeah, so here it is. d omega is the volume of the system divided by 2 pi squared k squared of omega dk of omega d omega. Now this k is the dispersion relation of the waves, so it describes the wave vector, and we don't know how this wave vector looks like. If we plot it, we have omega, we have k of omega, okay. And we know that it is behaving somehow. it is a function. It describes the properties of the wave propagation inside a media, inside our solid. And the assumption of divide is to use, for the whole range of omegas, okay, a linear approximation. Okay, so divide assumes, well, those phonons, they describe vibration. Vibrations are kind of sound waves that we have inside the system. So basically density fluctuations inside the system, not just some density fluctuations, but density vibrations and displacements that lead to standing waves. Okay. We know that those standing waves, they describe sound waves, at least for specific frequencies. So we are going to assume that it's always linear. Okay, so this is the divide approximation. This is where we stopped, I think, on Sunday. Now, if we look on the vector k, the displacements that describe the vector, they can be in the direction, so this is k. So the displacement, they can be displacement of the material that are in the direction of the vector of the wave vector. So if the displacements are in the direction of k, they are describing longitudinal displacements. Okay, so basically oscillations of waves that are longitudinal. But we can also have displacements with standing wave that are perpendicular to the propagation or to the direction of the wave vector. Okay, so those are, and we have two vectors. So for any given direction, general direction, there is always some specific longitudinal displacements which are in the direction of propagation of k. So there has to be only one vector that describes them, but there has to be two vectors that describe the transversal displacements. Right. So in total, when we compute k, and for this approximation, we have to use for this, because what this guy came from, where this guy came from. We looked on all the different standing waves, right? And we have we connected them somehow to the k, right? But the direction or different directions of the standing waves can be due to longitudinal waves, displacements, one for a specific perpendicular direction, and then another one due to a specific perpendicular direction. So in total, this density of state is not combining the three. This only describes one specific given direction, right? So in total, the density state has to be multiplied. If all of them are equal and identical, this density of state has to be multiplied by 3, generally speaking. Now, in theory, it's not exactly right, because what we know is that the velocity or the dispersion relation, even if we assume it's linear, so linear dispersion relation is simply stating, well, k equals 1 over the velocity. Let's use, that's not good enough. We have c, and we have omega over 2. So this is the dispersion relation we assume. Okay. Now, we have to look on 3 different waves, or wave displacements, or standing waves. So one coming from longitudinal displacements. So for this guy, let's call it the k, it's going to be 1 over c L omega. for the transversal, we are going to have, so let's call it K1. For the transversal, we're going K2. It's 1 over CT omega. And K3 is also going to be 1 over CT omega. So generally speaking, the CL and CT, which are the velocities of the waves inside the media, they are different. So there is a difference in wave velocities, which are longitudinal or transversal. Now we do assume that there is no inhomogeneity in the system, so the transversal velocities are independent on the specific direction. Okay. So let's see what we have. So we can have d1 of omega, which is v divided by 2 pi squared k1 squared omega dk1 omega d omega. We're going to have d2 omega, which is v divided by 2 pi squared k2 squared omega dk2 squared omega d omega. And we're going to have d3 of omega, which is v divided by 2 pi squared k3 squared of omega dk3 omega d omega. Now, d of omega, it is just a sum of the densities. Densities because there is a superposition of waves, so we can always add waves or the contributions of waves. So the density is just simply a summation of the different densities of the different waves states. So we have d is d1 of omega plus d2 of omega plus d3 of omega. Okay. And we substitute those values for the k's. So what we have v divided by 2 pi squared. K squared is always going to produce omega squared. Okay. And inside here, we're going to have, from d1, it's 1 over CL. And we are going to have also another 1 over CL squared from this guy. So it's 1 over CL to the third plus 2 multiplied by 1 over CT to the second. Okay. Now, in order to make it a little bit simpler, all of this, we're going to call it as 3 multiplied by 1 over C tilde, or just simply C to the third. Okay. So what we have, that the density of states d of omega is v divided by 2 pi squared omega squared multiplied by 3 divided by c to the third. So this is our density of states in the Debye approximation. Now, we do not assume that there are some fluctuations in the k of omega, and the dispersion relation is always linear. There is a superposition of waves. There are different velocities. We don't really care. We have an effective velocity. This is this c over here. Everything great. But we still have a problem. And we look on this density of states. There is something that's really annoying, right? Something that tells us, well, this can't be right. What's the problem with this density of states?
The powers.
Sorry?
The powers. Nothing.
The powers. No, nothing problem about the powers. Another guess? So what condition the density of states have to satisfy?
They will integrate to 1.
Yes. So the total, not about 1. 1, if it was probability function. Probability function, the integral has to go to 1. But the total number of states, if we integrate of all the possible omegas, has to give us 3n. So if we integrate from 0 to infinity of d omega, so we count all the possible frequencies, omegas that we have inside the system, it is the total number of states. What is the total number of states? the number of phonons that we have inside the states. But because remember, each omega represents a phonon. Okay, so the d omega of the omega is just the number of phonons around some specific omega. Right? And then when we go over all the different omegas, this has to give us 3n. Because we have 3n degrees of freedom, we have 3n phonons, quasi-particles inside the system. So this, it's kind of a normalization that has to be satisfied by any density that we come up with. And there is a problem with this guy, right? Because if we take an integral of omega squared d omega from 0 to infinity, this integral is going to explode. Right? So how debye solves this problem? How do you think debye solved this problem? What would you do if you were in debye's place?
Plotting the integral of something.
Yep.
There is no way to normalize the function, so maybe you just decide that it's 0 or something.
Yes.
You can just say that there's a maximum omega.
Yep. In some sense, cutting the integral. So debye said, well, great. I have this parabolic increase of the density of state, okay, and it actually goes to infinity. This is why the integral is exploding. Now debye will say, look, but of course I cannot take all the different omegas. I will have a cutoff. Let's call it omega max. Okay, so he called it omega max, and nowadays we call it omega debye, omega d. And the claim is, well, look, all of this is approximate theory, and it's not exactly correct for any omegas. Okay, so in any case, I'm not going to count all the different densities for very high frequencies. Okay, now moreover, extremely high frequency cannot be inside the media. Why? Because remember, omega is 1 over, proportional to 1 over the wavelength. All right. Now the wavelength of the wavelength of whatever of the waves inside the media. Now, if we assume that the media is continuum, so any omega is actually has to be possible. Okay, but what we have here, okay, so what is the original assumption? The original assumption is that, well, we know that there are atoms, the atoms doing something, but there is a distance between the different atoms. So it's not, I have voids between different atoms, right? So I cannot have waves that their wavelength is actually smaller than the inter-atom distance. So in any case, I cannot take this omega to infinity because I have a minimal lambda. Minimal lambda is related to the interatomic distances. Okay? And this is not 0, it's actually finite. So this is why I cannot have omegas or k vectors that are extremely high. In any case, I will have to cut it somewhere. And debye decided to cut it over here. Okay, so first of all, let's calculate this omega debye. So how we calculate omega debye? We just compute this integral over here. So an integral from 0 to omega debye of 3v divided by 2 pi squared omega to the second power divided by c to the third power d omega equals to 3n. Okay. So let's solve this integral. This integral is 3v to 2 pi squared c to the third power multiplied by 1 over 3 omega to the third power between 0 and omega debye equals to 3v divided by 2 pi squared c to the third power 1 over third omega debye to the third power. all of this equals to 3n. So we have omega divided to the third power equals to 3n multiplied by 2 pi squared c to the third divided by v. So omega divide, it is 3n or 6n pi squared c to the third v to the 1/3. So this is omega divide. Now everything is defined. We have d of omega. D of omega goes from 0 to omega divide. Omega divide is provided by this expression. So we know how many exactly phonons there are for each given omega. Okay. Moreover, we also know that all the different phonons are independent, and that the energy of the system is just simply a sum of the energies of all the different phonons that we have inside. Okay. So if you remember, we had two conditions. One, additivity of the energy. So the energy has to be represented as a sum of different energies of different particles. We have this. All the different phonons, the energy is just a sum of energies of the phonons. Part B, all the different particles have to be independent. Yes, all the different phonons. Well, I erased it, but this is actually what's coming from the description of the Hamiltonian. All the different phonons are independent because we have written down the Hamiltonian in a quadratic form. Okay. The moment that we have this, we know how to write the partition function. The partition function, z, is just multiplication over all phonons over zi. And what is zi? So instead of zi, we write z of omega. Because remember, so how we define a phonon? Phonon is a quasi-particle with a specific omega. Okay, so if we go and multiply all the different states, is basically or multiplication of all the different particles that we have inside the system. It's not a state. Okay, this is the factorization. We just multiply over all the different omegas that we have inside. Well, we cannot really multiply over all the different omegas because omegas are, I'm sorry, because omegas are what? Omegas are continuum, but for any given omega, we can compute this z of omega. Right? Now, we don't really need z for all the thermodynamic quantities because we know that f equals 1 over beta log of z. Right? So, and this guy is going to be minus 1 over beta, a sum over all omegas, log of z of omega. Okay. Now, this sum, we have to transform it into minus 1 over beta, integral from 0 to omega divide, okay, of what? Of 1 of z of omega, d of omega, d omega. So this summation, because omega is not discrete, omega is actually continuum. So for any given omega, there is densities. So this summation is transforming into the integration, and this is where we need this density of states that we also have. The integral from 0 to divide is simply due to the fact that d omega is defined only between 0 and omega divide. Right? So this is the form. We need to compute only z omega, and then, well, we will know z omega. We have a logarithm over here. We have a function that we know how it looks like. And we have everything. Well, we can have maybe a complex and non-trivial integral, but it's fine. It's already a technical question. Yeah.
How can we know the
How we can know what? Let's find out. Okay, so the only thing that it's not written on the board is what is z of omega. But you actually already know what is z of omega. Okay, so let's go back and here where Debye is basically looking on the solution of the Einstein model, and he said, yeah, I would like to perform something like Professor Einstein did. Okay? You look on a specific omega and you ask yourself, what are the different energies? So this is a particle, this is a phonon. What kind of energies this phonon can have? Okay. So the assumption is that it can have n multiplied by h bar omega. There are quantas of energies, okay, for a specific omega. Remember how we solved the Einstein model? This is the ideas of photoelectric effect. This is basically is saying, well, what is a particle? It's a harmonic oscillator, and harmonic oscillator, its energies are described by n plus 1/2 h bar omega. We omitted this 1/2 over here, and we have a number multiplied by h bar omega. Now, Einstein had no idea about quantum mechanics in 1907 and 1912, right? But he already claimed that there has to be a quantas of energies, because he used this approach in the photoelectric effect, and he used this approach in the Einstein model for solids. So Debye uses exactly the same approach. Says, well, I have wave, a phonon. What are the energies of the phonons? The energy of the phonons are coming in quantas of energies, which I'm saying this is some number h bar omega multiplied by an integer. This integer and can be 0, 1, 2, etc. So this is how you compute the z of omega. You basically sum up over all the different states of a phonon. So it's not convenient to use states instead, because we had states that describe this density of states, but this is states of different omegas, right? So remember that. And for any given phonon, for any given omega, we have density of states of the energies. Okay, different energies describe different states of a phonon with a given omega. Right, so states of different waves, and per wave different energetic states. And since all our phonons are independent, in order to compute the partition function of a given phonon, we have to count over all the different energies of this phonon. So this is e to the power minus beta n h bar omega, n goes from 0 to infinity. Okay, so this function, any questions?
I have a question about
Yes.
something way back. You defined CP and CL, right?
Yes.
A long time ago. When I have a planar wave, right,
Yes.
and let's say a sound wave, then the compression is, it's orthogonal to the direction that the wave propagates.
Depends. You can have waves that are orthogonal to the propagation, right? And they can be in the direction of the propagation. Transversal and longitudinal. There are two kinds of waves that can survive. And we counted all of them, right? And in 3D.
The existence of CP is weird to me.
Of CT?
Yeah.
Why?
Because when I imagine a wave, a sound wave, then I imagine a compression that moves in a certain direction.
Yeah, but you can think also about the displacements that are happening in perpendicular to the wave.
Okay.
So if you look on the wave, if you look on something, how the displacements can be arranged. So yeah, of course, the displacement can be in this direction, but the wave is propagating over there, and think about the springs that are oscillating in this direction. So think about springs. Springs can oscillate like this in 1D, or in 2D, they can oscillate like this, and they can oscillate like that. Okay? When you have lower dimensions, it becomes a little bit cumbersome. But okay. Let us get back to this guy. So here it's a sum, and it's a geometric sum. So we know that this is 1 over 1 minus e to the power minus beta h bar omega. Okay. So for the free energy, we have minus 1 over beta integral from 0 to omega Debye of what? Of a log of 1 over 1 minus e to the power minus beta h bar omega. And let's put everything inside, which is v divided by 2 pi squared. Where is this guy? 3. 3 2 pi squared omega squared divided by c to the third d omega.
סטאס, זה לא אמור להיות אומגה I, כי זה כל ההבדל שעכשיו יש.
Yeah, so you want to say this is omega I, which is great, okay? And if I had a very discrete spectrum of omega i's, then I would count of all the different omega i's over here, okay? But in general, I have a continuum spectrum of omegas. So for any given omega, I compute z of omega, right? And instead of making a summation, I'm making an integration. That's all. Okay. Now, where we are heading. So how we started all this divide approximation and etc. etc. The problem was that the specific heat in the limit of low temperatures, according to the Einstein model, wasn't behaving properly. It was decaying as e to the power minus something divided by t, okay? Where in reality it goes as t to the third. So our goal is to see this is our free energy, right? Can be obtained in the limit of t goes to 0, t to the third power, starting from this expression. Okay? So it becomes technical from this point on because we need to compute average energy, which is u, okay? And then we have to take the derivative of u with respect to temperature, which is Cv, right? So all of those operations are flexible to this nasty integral that we have inside. And when we take all the derivatives and perform all the integrations and take the limit of small temperatures or large temperatures, we want to see whether we're getting this, yes or no. Okay, so we have like 10 minutes, or at least let's start. So first is how we obtain energy. So there is an expression, of course, right? What is U? Minus, so if you don't remember what is U, you can always go and compute U from this guy, right? So what is U? Let's assume that I forgot all the formulas. Okay, I forgot them somehow. I know that E, any E, average, it's a sum over I, Fi, Ei. Okay. Now here I can compute the average energy for given omega, right? And then perform the integration over all the possible omegas. Okay. So of course I can shout to you the formula that relates the free energy to the average energy, but I don't want to do this. I want to go over again this procedure of how we compute different averages. Okay. So let's imagine that we have only one single phonon, one single particle. How I compute the average energy of this single particle, single quasi-particle. Okay? So if I'm having only one particle, so for a specific phonon with omega. Okay? So we have a given omega, and I'm looking only on this specific phonon. So I want to compute the average E of omega. How I perform this? I go and I can count over all the different states that this phonon can have. What are the different states? Different energetic states. So I'm counting from from 0 to infinity. The energy for each given n over 0 is n h bar omega, right? Multiplied by the probability of this phonon to be in this specific energetic state. So what is the probability of the phonon to be in state with given n? It's simply e to the power minus n h bar omega. We we have beta over here, divided by z over omega. So this is the probability. This is EI. This is the probability, and this is the value of the energy. Okay, so if I remember how the average is defined from probability 1 and 1, I can always, for a given particle, I can always compute it. Okay, so what is this? This is, we take 1 over z omega out, and we have a sum n goes from 0 to infinity of n h bar omega of e to the power minus beta n h bar omega.
It's the derivative.
And it is the derivative with respect to
Beta.
minus beta. So let's do it again. 1 over z over omega. Sum n goes from 0 to infinity minus d to d beta of e to the power minus beta n h bar omega. We take minus d over d beta out, and we have 1 over z over omega minus d to d beta, and here we have a sum n goes from 0 to infinity of e to the power minus beta n h bar omega. And this is z over omega. So 1 over z over omega minus d to d beta z over omega. So what we got is that E over omega average, okay, E over omega average, it is minus d over d beta log of z of omega. Okay. Now, I can go back to your question, and you ask me, well, you actually have omega I, right? So if I had a discrete spectrum, of omegas, let's assume that I had only 2 omegas in my system. Okay. So the total energy, I would have to go to the phonon with omega 1. The average, or the energy, is the energy of the phonon with omega 1 and the phonon with omega 2. Okay. So if I had only 2 phonons inside my system and the spectrum is discrete, the total energy is the energy with omega 1 and the energy of the omega 2, and the average energy is the average of the phonon with omega 1 plus the average of the phonon with omega 2. Okay. This goes for 2 phonons. Let's assume, and I will continue with your question, if I had many omegas, but they are still discrete. So if I have, let's say, n omegas, I'm going from I go equals to 1 up to n, E of omega I. Okay. Then the average is I goes from 1 to n, E over omega I, average. And the average of a sum is the sum over averages. So we have a sum I goes from 1 to n of E of omega I, average. And this is if I have a discrete spectrum. But what happens to the sum if I have an infinite number of different omegas? So as long as they are all independent, I can perform this summation. And in general, E total, so this is what I wanted to compute, the general energy is, instead of having a sum over here, I'm going to have an integration over E of omega for a specific omega, D of omega, d omega. The bounds of the integral are from 0 to d pi, omega d pi. So what we know is that this first step, remember, first step is to compute the average energy. The second step is to take the derivative with respect to temperature of the average energy, and then take the limit of small temperatures. And maybe let's see what also happens at large temperatures, right? But we have to do this for this integral. An integral from 0 to omega d by e of omega is this guy minus d to d beta of log of 1 over 1 minus e to the power of beta h bar omega multiplied by 3v divided by 2 pi squared omega squared c to the third power d omega. So what we have to do, we have to compute this integral, then we have to take the derivative. This is u. Then, so first of all, we compute this integral. Second of all, we compute du to dt. And then we take this in the limit of t goes to 0. Okay, so it'll take me something like half an hour to dance in front of you on the board. And we'll do it next week, right? So what we're going to do, at least at the beginning of the class, is compute a lot of different integrals, obtain Riemann zeta functions, and all nice stuff. See you on Sunday.